Hello everyone, welcome to Probability and Statistics for Data Science. In this video we're going to talk about regression, which is a fundamental problem in statistics and data science, where the goal is to estimate a certain quantity of interest from observations of other quantities. A very popular metric to evaluate regression methods is the mean squared error, which measures the average squared difference between the quantity that we want to estimate and our estimate. We're going to derive an estimator that is optimal with respect to mean squared error. It achieves the minimum possible mean squared error among all possible estimators. Let's get to it. We're going to talk about regression, and our goals are to introduce the regression problem and then derive an optimal solution in terms of mean squared error. So let's take a look at a couple of examples. In this example, we want to predict the rating for a movie, in particular for Independence Day, given the rating of another movie, in this case, Mission Impossible. So we're going to represent the rating for Independence Day as a random variable, and we want to estimate this random variable from the value of another random variable, which is the estimate for Mission Impossible. The type of data that we would have would be joint samples from these two random variables. In this case, other users, we would observe what ratings they gave to Independence Day and Mission Impossible. So here I'm showing you some examples. There were 12 users that gave a 2 to Independence Day and a 2 to Mission Impossible. There were, for example, 5 that gave a 5 to Independence Day and a 2 to Mission Impossible, and so on and so forth. From this data, we can characterize the joint distribution of the two random variables that represent both the quantity of interest and the observed quantity. And now the question is, from this joint distribution, how can we derive the best possible estimate of the rating for Independence Day given the rating for Mission Impossible? That's the regression problem. In this case, the two quantities are discrete because they can only take discrete values, 1, 2, 3, 4, or 5. But the problem makes a lot of sense also for continuous variables. So in this case, in this second example, we would like to estimate the temperature in Versailles, Kentucky, given the temperature in Corvallis, Oregon. We again model these quantities as random variables, and from past data, from past joint samples of the two random variables, so for example, here in this point, the temperature in Corvallis was almost 30 and the temperature in Versailles was around 15. Okay, so this is the scatter plot of past temperatures in Corvallis and Versailles at the same time. From such past data, we can estimate the joint PDF of the two random variables. Here I've estimated it using kernel density estimation. And now the question is, once we know this joint PDF, what is the best estimate of the temperature in Versailles as a function of the temperature in Corvallis? So that's the regression problem. We want to find a function h that approximates a certain random variable that represents our quantity of interest, given that we observe the value of a related quantity that we call a, or several related quantities. In that case, this would be a random vector instead of just a random variable. Now, an important question is, how do we evaluate this estimator? And this will depend on the specific application. So for example, if you want to predict movie ratings, you might care about different metrics than if you want to predict the temperature at a certain location. But a very useful general purpose metric is to just compute the squared error and average it over all possible values of the random variables. When we average it over all possible values of the random variable, what we're doing, so here, just to make sure that we're clear, this is the mean of the random variable b minus this function that estimates a from b, where we plug in the random variable a because we want to capture the probabilistic behavior of the estimator. That sounds very fancy, but what are we doing when we compute the mean of this quantity? We're just taking a look at the error for every possible value of a and b and weighting that error by the density, the joint density of the two random variables. This makes a lot of sense because for values that can occur very often, where the probability density is higher, we want to weight those more. If these were two discrete random variables, then instead of the density, we would have the joint PMF, and we would be weighting more values of A and B that occur more often together. So that makes a lot of sense. That is what the mean squared error is doing. It's averaging the squared error in a way that gives more weight to values that occur more. Hopefully that makes sense. So now we have to turn to the question of how do we derive an estimator of a random variable given another random variable when we know their joint distribution. So in order to get a bit inspired, let's remember what the best estimate is of a random variable when we know nothing except its distribution. We just have this, we want a constant estimate of the random variable that is optimal with respect to mean squared error. In a previous video, we saw that this optimal estimator, the best single number that I can give you to estimate a random variable in terms of mean squared error, is the mean of that random variable. Because basically it minimizes this function. If you remember, in the other video we took derivatives and we showed that the minimum is exactly at the mean. So now given that, what if you know that a related quantity is equal to a certain constant value? What estimator do you think we should use based on this idea that the mean is optimal with respect to mean squared error? Well, it makes a lot of sense to use the conditional mean of B given this event, right? That makes a lot of sense. We're going to see in a moment that indeed this is the optimal choice. But before that, let's make sure that we know what we're talking about. In a previous video, we defined the conditional mean function of a discrete random variable B given a random variable A as a function that maps the value of A to a weighted average of B, where we weighted by the conditional PMF of B given that A equals that value. If the random variable B is continuous, then instead of the conditional PMF, we use the conditional PDF. Okay? Intuitively, this is just the conditional average of B when we fix the value of A. And that actually sounds like a pretty reasonable estimate for the value of B if we know the value of A. So in practice, what would you do? Imagine that someone tells you that a user gave a rating of 2 to Mission Impossible. According to this estimator, you would want the conditional mean function of Independence Day given that the user gave a rating of 2 to Mission Impossible. How do you approximate that from data? This was explained in a previous video, but just to remind ourselves, well, you just estimate the corresponding past data where Mission Impossible had a 2. If we do this for all the possible ratings of Mission Impossible, we get this function, which is the conditional mean function of the rating for Independence Day given the rating for Mission Impossible, and that's what we would use for regression if we want to minimize mean squared error. We will prove this in a moment that this is optimal in terms of mean squared error. But, to begin with, let's understand what the estimator actually is. So if someone tells us, the rating for Mission Impossible is 3, then we would say, we predict 3.5. If the rating for Mission Impossible is 5, we predict 4.5. It seems that people that like Mission Impossible more also tend to like Independence Day more, but the relationship is not linear. You see that this is kind of linear maybe, but then there's a jump here. So it seems that people that really like Mission Impossible maybe are very generous in general and also give very, very high ratings to other movies, including Independence Day. At least that's my interpretation. But who knows? The point is that the trend is not linear. What about if we have continuous variables? Well, again, we're going to use the conditional mean function of Versailles given Corvallis to estimate the temperature in Versailles when we know the temperature in Corvallis. You can essentially do this in two ways. You can either estimate the the joint PDF of the two random variables and then derive the conditional. And then, for example, for the temperature where, if in Corvallis there's 10 degrees, you would compute the conditional PDF at Corvallis from the joint PDF and then just integrate to find the conditional mean function. Alternatively, as we saw in the video on conditional mean function, you can just take a slice here that is close to 10 and average the temperature in Versailles for those points. This is actually how I generated this estimate of the conditional mean function. And we see that it's pretty noisy here because there's not a lot of data, but in general, it makes quite a lot of sense. When it's warmer in Corvallis, our estimate for the temperature in Versailles is higher, but it's interesting. Once it's really hot in Corvallis, then we don't know anymore. This becomes constant. So again, the trend is not linear. We don't keep saying that it's hotter and hotter in Versailles according to this past data. Again, just to show you that the final predictor that we obtain is usually nonlinear. Excellent. So now we have an estimator, which is the conditional mean function, and I've been kind of hinting at the fact that it's optimal in terms of mean squared error. So now we're actually going to prove it. So again, we want to show that, I'm saying again way too much in the last videos, I don't know how to stop, sorry about that. We want to show that the conditional mean function minimizes the mean squared error when we average over the possible values of A and B using the joint density or the joint PMF of A and B, as discussed previously. Okay, it's this expression here. Among all possible h's, the conditional mean function, which is a function from A to B, minimizes this average error, this squared average error. So let's prove that. The way we're going to prove this is kind of like a typical technique when you want to compare two estimators, which is that you sum and subtract the estimator that you want to show is optimal. Okay, so this is the error of some arbitrary estimator, and now we're going to show that the error of the conditional mean function is smaller than, of the conditional mean is smaller than the error of that arbitrary estimator. So for that, we subtract and sum the estimator that we want to show is optimal, and now we're going to break this apart using linearity of expectation. So this expression is equal to the square of this guy plus the square of this guy plus 2 times the cross term. And then we apply linearity of expectation, so we have the expected value or the mean of each of these terms. In a moment, we're going to show that this guy is 0. This cross term is actually 0. If that is the case, then we're actually done. Why? Because these two terms that are left, one of them is the error of the conditional mean, which is the error that we want to show is the minimum possible. And we have plus another term that is non-negative because it's the mean of a non-negative quantity. So this immediately implies that this error of an arbitrary function is greater or equal to the error of the conditional mean, which is what we wanted to prove. Of course, we need to show for this to be true that this blue term is actually equal to 0. Okay, if we can show that that blue term is equal to 0, then we will have shown that the conditional mean is the optimal estimator in terms of mean squared error. So let's do that. We're going to take this term, which we want to show is equal to 0, and we're going to expand it. Okay, we just expand it and we apply linearity of expectation. Just to be clear, we multiply this guy times this guy and this guy, then this guy times this guy and this guy. Okay, so to get this very long expression, and then we break it up in terms using linearity of expectation. So now let's focus on these two last terms. All right, we're going to derive the conditional mean function of this guy inside here, and then we're going to apply iterated expectation. So what's the conditional mean function of HA times B? Let's assume things are continuous. If they were discrete, the reasoning is almost the same. So by definition, it's that function multiplied by the conditional PDF of B given A, and we integrate over all possible values of B. Okay, so now what happens? Well, this guy happens to be constant with respect to B, so we can take it out. And what do we have here? Well, this is just the conditional mean function of B given A. So we have shown that the conditional mean function of HAB is equal to HA times the conditional mean function of B given A. Why is that important? Well, by iterated expectation, the expected value of HA times B is actually equal to the expected value of its conditional mean. But the expected value of its conditional mean is actually the expected value of this guy, because we have proved here that it's equal to the conditional mean. And what do we have here? Well, we have here the expected value of HA times B, and here we have essentially the expected value of its conditional mean. So by iterated expectation, those quantities are the same, they cancel out. Okay, so we've done, we're done with the third and fourth terms. What about these guys? Well, here we're going to remember that the conditional mean function is actually a function of A. So in particular, we could plug it in here and apply this identity that we have proved. So the mean of the conditional mean function of A of B given A times B is equal to the mean of this conditional mean function of this function. So this can get a little bit tricky, but let's just think of this as some kind of H, okay, H of A times B, right? Like if you think this is H of A times B, and you can do this because the conditional mean function is a function of A, then essentially, because of this identity, we know that this is going to be equal to the expected value of that function, which is the conditional mean, times the conditional mean. So it's just the conditional mean squared. Okay, so maybe it's easier. I mean, I'm sure this is easier for you to just write down and follow step by step. But my point is that if we apply this, where we replace H by the conditional mean function, we obtain this, which essentially tells us that this value is equal to this value. So they also cancel out. Again, I don't know how, hopefully that was kind of clear. I recommend that you just write it out by yourselves. The bottom line is we apply iterated expectation, and we remember that the conditional mean function is a function of A. So now we have actually proved that this term is equal to 0, and because of what we said previously, that establishes that the conditional mean is optimal in terms of mean squared error. You cannot find another estimator that has a smaller mean squared error than the conditional mean. Let's do an example. Here we have the joint PMF of the number of cats and dogs. This is a made-up example, it's not real data. I looked for some real data, I couldn't find anything. If you know of any data sets, let me know, but this I just made up. So in this fictitious town, this is the probability that someone has 1 cat and 0 dogs, 2 cats and 1 dog, and so on. And now we want to predict the number of dogs that people have based on the number of cats. What are we going to do? We're going to use the conditional mean function because we know that that's optimal in terms of mean squared error. So for that, we need the conditional PMF of C given D, which is here. What have we done, by the way? We have just normalized the rows so that they add up to 1. Okay, this is how we obtain the conditional PMF from the joint PMF, in case you don't remember, but we have a video on this, so you can check it out. And now, if we want the conditional mean of the number of cats given that there's 0 dogs, what are we going to do? We're going to compute the mean according to those probabilities. We're going to sum all the possible values of the number of cats times the conditional probabilities given that there's 0 dogs, and the result is 0.77 cats. We can do this again using this row when people have 1 dog. That mean is 0.4, and when people have 2 dogs, in my fictitious example, they have less cats, the mean is just 0.29. Okay, and this is the optimal estimate based on that joint PMF in terms of mean squared error. Now you could say, let's compute before I go. You'll see where I'm going in a moment. Before that, let's compute the mean squared error of our estimate. It's always good to do concrete examples and see what these quantities that we have been moving around in proofs actually are. So here we want the mean of the error between the number of cats and our estimate of the number of cats. So what is this? We're going to sum the possible number of cats and our corresponding estimates for all possible numbers of dogs, and we're going to weight this by the probability of observing those number of cats and those number of dogs. And here is where the mean squared error does something that makes a lot of sense, which is it weights more, for example, the situation where there are 0 cats and 0 dogs than the situation where there are 2 dogs and 1 cat, because that happens more often. So this is weighted in this way in the mean squared error, which makes quite a lot of sense. Okay, so we're going to take, for example, 0 minus 0, and we're going to weight it by the corresponding probability, which is, no, not 0 minus 0, 0 minus 0.77, which is our estimate when someone has 0 dogs. We multiply it by the probability that there's 0 cats and 0 dogs, plus all of this until we reach here, where we have that the truth is 1 cat. We have to compare it to the conditional mean when there's 2 dogs, which is 0.29. We square it, and then we multiply by the corresponding probability. Okay, so that's what we do for all the entries. Here I do recommend that you kind of work it through and see if I made a mistake or not. What you will see is that, hopefully, the mean squared error is equal to 0.76. So now what I wanted to say before is that it might sound weird to estimate the number of cats as 0.29 when you know that people can have either 0, 1, or 2 cats. And in some situations, you might not want to do that. You might actually want to predict whether people have 0, 1, or 2 cats. That will be more of a classification problem as opposed to a regression problem. And we're going to see how that solution would do for the regression problem. So there, a reasonable thing to do if you want to choose between just 0, 1, or 2 is to choose the value that maximizes the conditional probability of that number of cats given the observed number of dogs. So let's take a look at what that estimator would look like. So if someone has 0 dogs, then the probability that they have 0 cats is 0.54, the probability that they have 1 cat is 0.23, 2 cats 0.15, 3 cats 0.08. So if we want to just choose between these options, the most reasonable option is 0. Okay? So because it has the highest probability. If we do that when someone has 1 dog, again 0 has the highest probability. If we do that when someone has 2 dogs, 0 has the highest probability. So this classification approach essentially always says that people don't have cats, because that's the most likely conditioned on any number of dogs. Now let's take a look at the mean squared error of that alternative estimator, which is not optimized for mean squared error. It's not optimized for regression. It's optimized for classification. So what do? We look at the actual number of cats and we subtract our estimator based on the number of dogs. And again, we weight it by the probabilities because we want the mean squared error. Okay, so this is what this is going to look like. Notice that this guy is always 0, so essentially this is going to be the probability of C and D times C squared summed over all of the possible values. It turns out that that is equal to 1.19, which is indeed higher than the minimum mean squared error estimator, which is the conditional mean. And that's not surprising because we've proved that this always has to happen. Like we cannot find an estimator that has smaller mean squared error, because we proved that that is impossible. But it's, again, good to see that it works out for this particular example. Also, so that you see actually what these quantities that we manipulated in the proof actually look like for a simple example. All right, so from everything I've said, it seems that regression is a solved problem. So is regression like trivial? Have we, solved regression? That's it, we can go home? Well, actually, no. Because we have been looking at examples where we had a single feature. And for those situations, it's actually true that if you are able to estimate the joint distribution between the feature and the quantity that you want to estimate, then you should use the conditional mean. That's going to be optimal in terms of mean squared error. You are done. That's the best possible estimate for that metric. However, when you have multiple features, it's not so easy. What is the problem? The problem is that it's usually intractable to estimate the conditional mean due to the curse of dimensionality. This is best seen through an example. So imagine that we're in our movie example, and instead of just based on the rating of Mission Impossible, we want to estimate the rating for Independence Day given 100 movies that someone has seen. And that's not a weird example, right? Like this Netflix, people watch many things on Netflix. It's highly likely that someone is going to have watched 100 different programs or 100 different movies. So there, what problem do we have? Well, we need the conditional mean for every possible ratings for these 100 movies, how many possible ratings are there? Well, they scale exponentially with the number of movies. So there's 5 to the 100 possibilities of different ratings that someone could have given. So when we go to our database, typically what's going to happen is we're never going to find people that gave exactly the same ratings as this person to these 100 movies. This will never happen because there's too many movies. This is the curse of dimensionality. And we have a video on the curse of dimensionality that you can take a look at. So the good news is that the mean squared error is optimal for regression. The bad news is that you cannot, no, not the mean squared error, sorry. The good news is that the conditional mean is optimal for regression in terms of mean squared error. The bad news is that you can often not compute it unless the number of features is very small. So many methods in machine learning try to approximate the conditional mean in this situation where, because of the curse of dimensionality, you cannot compute it exactly. All right, and that's all I got. What have we learned? We have learned that the conditional mean is an optimal estimator for regression, and we have also learned that when you have many features, it may not be possible to calculate it, so it's not all good news. Thank you very much.